So now I can hear you. So today we're going to continue what we stopped last lecture, which is about the steam table and how to use it. Okay, guys. So let's open the problem. Is in the end of lecture 3. We have about like 60 problems. We're going to solve 2, 3 of them. So please help out me to finish them as soon as possible. As you can see, please open lecture 3, page 37. This is yes, lecture 4, but we're going to look again problem 323, for example. If you look at problem 323 in page 37 in lecture 3, the very end, I give you a table. You will see that in the midterm and some quizzes give you like temperature, pressure, specific volume, and phase description or phase status. I give any two. We said before, instead postulate that we need at least 2 independent intensive properties. So I need to give you any 2 properties. For example, the first row, I give you the temperature and I give you the volume. You can get this, you can get this. How? At this temperature, from table A4, you can get VF and VG. We said F is always liquid, G always the vapor. And compare it with this guy. So you have 3 cases. You can be either here, compressed liquid lower than VF. You can be here in between. It means you are mixture. You can be here, superheated vapor, greater than any of them. So your volume is so big, even greater than. So if you plot it, this is pressure, for example. You can be here or here or here at the same temperature. This is temperature. You can be either lower than VG, VF, in between VF and VG, greater than VG. It means you are superheated vapor. At this temperature, you can get the description, maybe here. Then, if you want the pressure, this is the saturation pressure. At this temperature, 120, you can get P saturation, the second row, the second column. Okay, clear, guys? Table A, open table A4 at this temperature, you can get the VF and VG. Clear? Somebody
Yes.
say yes or no?
Yes.
Great. So the same for the second problem. He said, for example, the second problem, he said, no, I'll give you pressure and the status, like saturated liquid. So they give you pressure, saturated liquid. Yeah, you can get everything. Saturated liquid, guys, what does quality here is? Quality is what? Can somebody tell me what the quality? What is the quality? So this is constant, for example, temperature line in PV diagram. I said this is a pressure line, constant pressure. For example, this is the pressure. I'm saying saturated liquid here. What is the quality, guys? Quality is what?
Is
0.
T? Oh,
quality is 0. So I can get the temperature, T saturation. I can get the specific volume, which is VF at this pressure, and X equals 0. So at saturated liquid, X equals 0, quality 0. At X equal 1, quality is 100% saturated vapor. Okay. The same for the table 26. Please read for me the title of 326. The title. That's the title of problem 326. Anyone read it? The same page 37. Please read the title of problem 326. Hey guys, are you alive?
Yeah. Complete this table for refrigerant 134A.
So this refrigerant 134A, refrigerant fluid R134A, is a fluid like water, pure fluid. Like for example, oxygen can be also pure fluid. Nitrogen, air, any fluid, we can produce a steam table. We can get some fluid from liquid state, heat it up, evaporate, plot, or get the table. Go please, if you go to the tables, you'll see table, I think A11, A12, A13 for this fluid R134A, refrigerant 134A. It is a fluid that used in refrigerators, freezers, R134A, very famous fluid. The same for air, for example. I will give you example, quick example about air. If you got air, if I give you air, which is I think like 80% nitrogen, 20% oxygen, like less than 1% CO2, carbon dioxide, some argon, some other fluids, some other gases. So this is, we call it pure air, air. Yeah, it's a mixture, but let's say it's air. So this air, at for example, minus 120, it will be a liquid. Has a steam table like this. So if you have a liquid air, heat it up, constant pressure, not atmosphere, you'll see something like this. This is 1 atmosphere for air. This is a TV diagram for air. So if I give you some air, if you cool it down or cool it down until minus 20 Celsius, for example, you will see it became liquid. Minus 12, 200 Celsius will be a liquid. Maybe 250 will be a solid. If you keep adding heat, this volume will be so small. When you heat it up, it will be like a huge, which is 1,000 times, which is air. So this is air, but this is liquid. From a small size to big size, from V equal 0.001 to almost 225, I think, kilogram per meter cube, which is density with this 1 over it's a rho. So from very small specific volume to very large specific volume, almost 1. The density or the specific volume of air around 1. Unlike water is 1,000. The density, which is 0.01 for specific volume. So what I want to say here is what? Do you know where we live, guys? Where we live? Where now we are living? We are living here. This is our life. We see always air is what? Is gas. So we are living in the superheated region of air. Our life, our standard temperature and pressure is the superheated region of air. You got it? So we are living now in the superheat. This is air surrounding us, superheated region of the air. So get air at minus 200 Celsius, which is, we're not living here. Keep the pressure constant, 1 atmosphere. Add heat. You got the same table. We are here. We are living here in the superheated region of air. We're going to talk a lot today about air, about ideal gas law or gases in general. Okay, guys, clear? So for every fluid, we have table. For every fluid, like this R134. Please go ahead and get the data the same way I get you from A4, A5, A6, A7. A4 temperature input, A5 pressure input, A6 superheated vapor, A7 compressed liquid. So for problem 28, we're gonna solve this problem. Let's solve it. 328, the same page, the last problem in this page. I'm gonna solve it. Let's solve it in with numbers. So read it out loud for me, please. He said, I give you a 1.8 meter cube tank, rigid tank. Rigid tank, guys, it's a very important keyword in your life. Rigid tank, do not leave it. This is a very important word. This means volume is constant, mass is constant, always. So I give you a rigid tank. When you read this word, means volume always constant and mass always, the total mass, the total volume. Yeah, maybe some liquid, that is problem, and some vapor, it's okay, or all vapor, or all liquid, it's okay. But the total mass, it's rigid. Nothing going in, nothing going out. It's a rigid tank. Nothing going in, nothing go out. Closed system. Control mass. Mass is constant and volume is constant. Total volume is given 1.8 meter cube. It's always. 1/3 of the fluid, the volume is liquid phase. Guys, the quality is based on mass. Quality is mass of gas over total mass. But here he give you volume. Do not be following this. This is a trick. This is 1/3 of the volume. So the VF, total VF, is 1/3 total V, which is, for example, 1.8 meter cube over 3. It's about 0.6 meter cube. Liquid, while the gas is 2/3, which is 1.2 meter cube. This is not quality. Do not divide this by this. Don't say 1/3 quality. That's wrong. That's not quality. This is mass based, volume based. Quality is mass based. This is vapor. So this is the quality, the volume. Here we have 1.8 of the volume. 1.2 of the volume is vapor, while 0.6 volume is liquid. Determine. Find for me. This is temperature. Temperature here, sorry, this is typo 22 Celsius. This is not 8, this is Celsius. When I printed it was mistake. Celsius. 220 Celsius. So this 8 is the degree centigrade. So here I give you almost two things. I told you this is mixture. I give you volume and temperature. So with mixture and volume, and even with this fraction, you can get the details of the rest of the data. Sorry. So what we need here, he wants determine A, I want pressure. Let me write it a little bit here to get space for you. I want, please here, determine for me pressure. Determine for me quality. Quality is not 1/3. The density of the mixture is 1/nu of the system density. Okay, that's problem is simple, but it needs some concentration. You need to focus how to use the table, how to understand the problem. From the first word, rigid tank, you got a lot of things. From the volume fraction, you can get this V and this V, of course, and give you the temperature. So what happened before I start? If I just plot my curve, this is certain temperature, pressure. I don't know where the pressure is yet. Let's say this P. For example, this is a constant P, whatever it is. I'm sure the temperature here is 220. And he said this is some part liquid, some part vapor. It means what? It means compressed liquid, mixture, or superheated. It means what? One word means what? Compressed liquid or mixture or superheated vapor? Say one word, please. It's a mixture. Something here. Something is here. So simple. Because he gave it to us some vapor, some liquid. So at this temperature, I can easily get the P saturation. Go table A4, please. I get for this water, if it's water, if it's some other fluid, go to the corresponding table and find the saturation temperature and this pressure at this temperature at 220 Celsius. What is this, guys? Open brace table A4 and tell me what is this. Somebody tell me. Say to me, what is this? Somebody?
2319.6.
2320 kilopascal. Perfect. Perfect. This is almost 20 atmosphere at 220 Celsius. This is a temperature, saturation temperature, saturation pressure. Now, in order to get the quality or volume or anything, we know this point, if it's completely liquid, will be here. This is called VF, for example. If it's completely vapor, I will be here, VG. Specific volume at, but I'm in between. I'm in between. Some liquid and some vapor. So here, the properties always for this G. The properties here always F. In the vapor G, in the liquid F, always. It means, if I told you this is VF, VF equals, what is the VF? At this, VF was 0.001190. 0.001190. This is what? A specific volume of the liquid phase. 001. I told you you're gonna see it a lot. Always when you see that, relax. You are correct. 1,000 kilogram per meter cube, almost. So this is VF. I have a V. The derivative of VF is mass over mass or over volume. So I have the volume. I can get the mass. The same for VG. We have a specific volume G. I can get it. At this temperature, VG was 0.080, 0.0809 something meter cube per kilogram. I can get also mg. I can get from here mf because I have the volume at this state. And this is a state. Maybe if I add heat, it's okay, rich tank, yes, but I can add heat. I can take heat. So it will be different. It can go here, it can go here, it can go here. But at this point, at this state, certain state, I know the V, total volume, a total volume, I can get the mass. So if I want X, somebody tell me the equation of X, guys. X is what? What is the definition of quality?
V minus VF over VG minus VF.
Yes, that's a way. V minus VF, but we don't have VF yet. We can say the original definition, which is mass gas over mass total. I do not know where this point is yet. I don't know. But I know exactly the mg. I know exactly mf. That's great. Go to the original position, original definition. Do not forget the original definition, which is the quality is the mass of the vapor over total mass. I already have mass vapor. I have a specific mass, a volume, and I have total volume, corresponding volume. I have a specific volume and the corresponding volume of the fluid and gas. So I have the masses. V small is V M over V capital. So I can get the masses. Here, how many kilograms? How many kilograms or grams? Use kilograms. So you can get the quality. Is it easy, guys, or hard? For this problem, the quality was 13 point, I think, 0.0269. 0.0269. Oh, this is a quality. A very, very, so if you fall in a mistake by saying the 1/3 is the quality, that's wrong. This is 0.33333. This is volume ratio, that's wrong. The quality is based on mass ratio. How much mass of the vapor to the total mass. or even here, actually, this is 2/3 for the gas, even worse, 0.6667. So do not fall. X is mass base. Remember this, X is mass base. Mass of the vapor over total mass. We have a little bit vapor at this status, at this point, state point. The last one, rho, or the density, or nu. How can I get rho, guys? I need to get, first, I need to get what? The nu. How can I get nu, guys? Can somebody tell me? How can I get nu? The specific volume. The specific volume, guys. Can I find it? How can I find the specific volume of this status?
Divide by the mass.
Yeah, the total mass over total volume. So can I say mg plus mf over the total volume, which is always constant, 1.8 meter cube, or vf plus x vfg. Remember this? You have quality. You have this way. Actually, no. Actually, it's a volume over mass. It's a volume over mass, which is v over mg plus mf. This is specific, so divide by mass. So it's either volume over mass or Vs plus X VFG. And you have Vf, you have VFG, which is the difference here, bigger minus smaller. And you have X, you can get V. Rho, what I want is 1 over nu. Here it was, I think, 287.5 meter cube, kilogram per meter cube. This is the density. A density. Okay, guys? Clear?
Yes.
So please go ahead and read problem 41. Turn the page 38. Read problem 341. Does anyone have any question this problem first before I turn the next problem? Any questions?
Someone says to go over the mixture part again.
Okay. So any state can be either compressed liquid, mixture, vapor, saturated vapor. So mainly it's compressed liquid, mixture, and superheated vapor. He gave me the temperature. He said 1/3 is liquid. Of course, the 2/3 is vapor, in volume base. And he gave me the tank volume. Because he said some part liquid, some part vapor, it means it's a mixture. No way. He said that in the problem. 1/3 of the volume is liquid. It means mixture. Without any thinking. You have some vapor, some liquid. This is the current state. So I get very easily saturation pressure from table A4. You're supposed to practice. You have a quiz. You're supposed to practice how to get something at the corresponding temperature or pressure or volume. So you got saturation pressure at 220 Celsius, which is 2320 kilopascal. 2320 kilopascal. I want to quality. Quality means you can get it from several ways. Either V minus VF over VFG, the same U minus UF over UFG, H minus HF over HFG, S minus SF from all definition, or mass over total mass. So mass of the vapor over total mass. This is the only two ways, from the original, the current value minus VG over VFG, U minus UF over UFG, whatever, it depends on the data you have. So what I can get the masses. So how can I get the masses? From the VF, I have VF from at this temperature. If you go to table A4, at this temperature, you can easily get VF, VG, specific volume F, specific volume G, UF, UG, HFG, everything at 220 from table A4 or table A5. Saturated values. And you have the total volume of the liquid. volume of the vapor. It means you can get the mass of the liquid, the mass of the vapor. So you have the mass here and the mass there. You can get anything now. Any G is vapor, any F is liquid. So mass of G, which is mass vapor, over total mass give you quality. How much mass of the vapor. Finally, the specific volume or density specific volume is here, which is VF plus X VFG. That's the definition we'll give derived in the very end. This equation is so extremely important. You will see it at the end of the course. Anywhere you have mixture, you see this. Anywhere you have mixture, like steam engines, steam turbines. We're gonna take a lot of engines. New, this can be U, H, S, a lot of things. Internal energy, enthalpy, entropy. We're gonna talk about entropy. Specific volume. Here is specific volume. I have VF at this temperature. I have VG. I got the quality, so I can get how much the specific volume. But I don't actually want this. I want density. So density 1 over nu, so I can get the density. Clear? Clear, guys?
Yes.
I know I'm repeating a lot because I'm not in front of you. So I'm trying to give you as maximum inputs from my side as I can. I maybe you don't see behind the scene, but there is a lot of efforts to do that. Okay, guys, please write behind me because this solution does not, this solution do not exist in the lecture. So you need to write them down. Make sure you can able to understand and solve some of the problems yourself. Problem 41, the same way we need to, when you read the problem, you need to understand what's the inputs. Problem 41.
Question.
Yes. Yes, go ahead. What's your question?
Is there a way for you to like move the camera closer to the whiteboard? Some of the text, some of the stuff you're writing out, I can't read it.
Okay. Maybe you need a glass like me. I'm gonna do that. 1 minute. One minute, guy. 1 minute.
Okay, thank you.
No worries. I wish that works. Ah. This is the closer I can do. You'll see me upside down. Okay. I'll try. Ah, that's so hard. 1 second. 1 second. How about now?
Yeah, it looks a little better.
Little better. Okay. This is the thank you. Okay. Welcome.
Yeah, it looks good.
I'm just kidding. You don't worry. Don't worry. No problem. I am always open for any criticism from any type. Any type, by the way. So anytime you see something wrong, tell me. This is the way I improve myself. Okay. Anytime, please. Don't hesitate to tell me that I'm bad. I know that. Okay. So problem 41, which is so simple. Read it, please. Page 38. It says you have 10 kilogram of R134A. That's a good exercise because this is another fluid. Table A11, 12, 13. So we have 10 kilograms of R134A, refrigerant 134A at pressure of fills a rigid container. Rigid means volume is constant. Always, when you hear this word, mass is constant. Always, this need to be right up in your mind when you read this word, keyword. Determine the temperature and total enthalpy. Give me, please, at this case, I need temperature determined first. A, temperature. B, I want enthalpy. Total enthalpy means big H. So the first stage you can get H small, then mass times H small give you H capital, which is the total enthalpy. The specific enthalpy in the tables. Multiply by mass, go back to the extensive property, which is total enthalpy. The second part, he said, okay, this is state 1. This is a tank. I'm gonna add heat. It's gonna go to state 2. State 1, I have pressure, I have 10 kilograms, I have rigid tank, I have mass. And he said this tank actually 14 liters. If you look at the figure, please, it's also in the given. 14 liters. So you have the mass and you have volume. Now, state 2 is pressure now is 600 kilopascal. And he said, find for me, this is state 1. This is temperature 1, H1. Find for me here at state 2. Find for me A, T2, B, H2. Clear, guys? So we have here 2 problems, not 1 problem, 2 problems. That's very good. We need to find T1 and H1. But we need to make sure that we have 2 independent intensive properties. If you have 2 independent intensive properties, you're great. You can get everything in this state. The same here. If you have 2 independent intensive property, you can get everything in this state. By name and address, you can get this guy, exactly this guy. Only by name you cannot, by address you cannot. You need both of them. Let's go to state 1. State 1. Think carefully. This is a rigid tank. I give you the mass and the volume. That's so simple. So I have pressure P1 first. I need something else, so I get everything about this state. One thing, independent of pressure. He gave us mass and volume, which means new, a specific volume, which is volume over mass. 14 liters over 10 kilograms, which means 0.000014 maybe. This is 00 like this. Meter cube per kilogram. Yes, we got it. So we have 2 independent properties. Please go ahead and table, I think A11. Open with me a table A11 in the given new lectures, in the files, lectures. So please open with me, follow me. Open with me, please, the Steam table, which is, I think, I can share with you if you want. Do you want guys to share with you a screen?
Yes.
Sure, no worries. So table A11, I'm gonna share the screen now. Let me open, share screen. So look at this row, A11. Can you see A11? So saturated refrigerant 134A, table A12, pressure based, temperature based, and pressure table. Superheated. Can you see? pH diagram. So go ahead and table A11. Go down the very bottom after the water. A11, which is what we are looking for. We have pressure and we have volume. Yeah, this is table, I think, A11. But we have pressure and volume. Do we need to? We can go here with temperature base? Nope. We need to go where? Pressure base, which table? A12. Go to A12. Here, this is the A12. This is pressure base for this fluid. We have pressure inputs here. We have pressure inputs here. That's why we prefer table A12, because this is a pressure base. Let me share with you again. So at this one, we need 300 kilopascal, correct? This
Yes.
guy, something between this and this, interpolation. Anyway, actually the good news is 300 means average. So if this is 280, this is 320, if you're smart enough like me, of course, you can just take 280 plus 320 over 2. Make sense? It means if you want VF at 300, just take this VF plus this VF over 2. Easier? Correct?
Yes, way easier.
Yes.
Oh, of course, you are engineer. That means you are always using your mind to do something. So here it's easier to do average, easier than interpolation. So from this data, as you can see here, your specific volume is in between this value. It's 0.00076, 0.000, 0.06, 0.07. So it means this value recommended that your case is in between VF and VG. So you are what? You are what, guys? You are what? This value is 0.000 something. This is, I think, 00 something, 6 or 7. So this means you are mixture. You are what? So if you plot, for example, the PV diagram, temperature line, something like this.
I can't see what's on the right.
Okay. So, oh, I see. I know. Sorry. Yeah, you can say it, guys. I said to you anything. So your volume, your specific volume, is in between these two values. Is in between these two values. The VF, which is the average between 320 and 280, get VF. Average here, it's for example, here is 0.0001 something. Here is 0076 something. So your value is in between. Your value is in between. This means you are a mixture. So if you plot, for example, the PV diagram, this is a constant temperature line. This is temperature is constant. Let me plot it with other color. Whatever it is. So where is the point, guys? Can somebody tell me where is it? It's here or here or here? It is where?
Somewhere in the middle.
A mixture, exactly here. Somewhere here, like for example here. So this one. Yes, we can get everything. First of all, you have V1, new one. You have this. You can get the VF, just average. Get VF at 280 plus VF at 320, divide by 2. This is interpolation. Here, the VG at 320 plus VG 280 Celsius, divide by 2. These guys are given in the table. Let me open the table again. Please look at the table. Here, you have VG, VF at 320, VF 280, VG 320, VG 280. Make sense? Make sense?
Yes.
Perfect. Now, if you said that, you can see the screen now? You can see the board?
Yes.
So here, you have VF here at 300 kilopascal. You can have this VF and VG This means you can get x. X equal V, which you have, let's say x1, V1 minus VF1 over VG1 minus VF1, which is VFG. You have everything. You have V1, you have VF1, you have VG1, you can get x1. So this one is this one. This one from the table, from averaging or interpolation, as you wish. It's up to you always. So interpolation is always faster, is the correct. Sometimes it average, sometimes like this simple case. Make sense? Guys?
I had a question about your V of F.
Yes, go ahead.
For that second fraction down there, is it 220 plus, yeah, VF 220 plus VF 320 or 280? Oh, okay, I see.
This one? You cannot see? You need to have a glass.
Oh, yeah,
correct.
now I see it.
It is correct from the beginning, but you don't see it, okay? I'm just kidding. Anyway, so this is 280 plus 320 because you have two rows, 280 and 320, but you don't have, I want 300. So something in between, average, exactly average. If it was not like that, need to do what? Interpolation. Now, I did not get what he wants. He wants T1 and H1. So what should I bother to do? T1 is what? Simply is T saturation. Correct? At this pressure, the same table, you just say the same table. Here, this is the temperature. Negative 1.25. Actually, no. The average between these two. Negative 5.38 minus 1.25 divided by 2. The average between these two values. You got it? Because I want 300. So T1, let me stop sharing, please. So T1 is simply, again, T1, which is T saturation at 320 Pascal, T1 T saturation and 280 divided by 2. So it's minus 5.83 minus 1.25 divided by 2. It's get like 3.5 or something. Celsius. Make sense? Make sense? Guys?
Yes, it makes sense.
Okay, H1. Let's go up a little bit here. H1. H1 is HF plus X HFG. Everything is 1. 1, 1, 1, 1. You have H this. Average between 320 plus 280. Guys, I got tired. Okay? Always do that yourself. Here, get HFG 320 plus HFG 280 divided by 2. And you have X1, you can get H1. But he doesn't want H1, the specific. He wants the total. So total is what? Total is what? Is mass times specific. And you have the mass multiplied by 10 kilogram. It became, here it was kilojoule by kilogram. Here it became kilojoule. This is the extensive, this is the intensive properties. Step 2, he said, I'm gonna add heat. I'm gonna add heat to the system. Here, adding heat. I give you only a pressure. I want temperature and enthalpy. How can I get them, guys? I give only pressure. Something is missing. No. This is rigid tank. What is this rigid tank? It means the volume doesn't change. The mass doesn't change. It means a specific volume does not change. Whatever you got there is still there. It's still the same. So here, can somebody tell me, how can I move in this chart? In this chart, how can I move? Where is the constant specific volume line? Where is it? This is constant pressure line. This is constant temperature line. Where is the constant volume line? Say one word. Hello, guys. Hey, guys. So let's, the computer was feeling you. So let's take 5-minute break. We're gonna come back at 11, okay?
All right.
Okay.
At 11. Thank you. I'm gonna go back at 11, guys. See you guys in 5 minutes. Hello, hello.
Hello.
Okay, good. So in this problem is state 1. We said we don't know, so we have a pressure. We have a specific volume from volume over mass. It was in between the liquid and the vapor at this pressure. It means mixture. And we can get everything. You can get X, you can get everything else. Temperature is the saturated temperature. Enthalpy from the weighting here, you can get from this one. And you can get anything else. If you want total property, extensive property, just multiply by mass. So kilojoule per kilogram became kilojoule back. The total enthalpy. State 2, he gave only pressure. But I can get everything because this is rigid tank. This is what? A rigid tank. Rigid tank means the specific volume does not change. V1 and V2 are the same. Or Nu1 and Nu2 are the same. So we need to move here what? Vertically. This is 1. So upward or downward, guys? I'm eating heat. Pressure build up or decrease?
Builds up.
So if it's of course here or maybe here. Maybe this line a little bit to the right and it was here. Like it goes from this point to this point if it's a little bit right. But the quality is a little bit small. So at a little bit closer to the VF. The higher quality, the closer to. So this is 0, this is 1, the quality. So it can go up maybe here. Maybe go up, it goes here and superheated. So let's say for now this is 2. And how can I know that? You have the pressure. This is the pressure here is 600, correct? Check VF and VG. If your volume, which is the same specific volume because rigid tank, between these values, you are mixture. If it's bigger than this, it means you are saturated. You are superheated. So it depends on this value. If Z between this and this, mixture. If it's a greater, superheated. Lower, compressed liquid. Make sense? Please go ahead, the same table, A12, check this pressure, find VG and VF, and find yours. You'll find yours in between. It means you are mixture. But your X became bigger. So let's say X here was, for example, 0.1, here can go to 0.3 because this curve is getting closer. So it can be much larger here because you get more. It can be even 1 or even greater than, not greater than 1. It means more than VG, superheated, okay? So I'll let you do this part. If you want D2, it's most of all this is saturated, so it's desaturation. You want H2, you need to get H2 first. First, you need to get X2, then you get H2, then get H2. X2 from volumes, V2 minus VF2 over VG FG2. TH2 is HF2 plus X2 HFG2 at state 2. HF2 plus X2 HFG2. H2 just mass, which is the same mass doesn't change. 10 kilograms times H2 enthalpy 2. So the mass does not change. This is rigid tank. The mass does not change. Now, let's go lecture 4, which we are talking about gases. Ideal gas. Any question, guys? Do it yourself and solve the rest of the problems, please. Gas. Ideal gas law. We have just less than 30 minutes. We need to solve. We need to give some introduction for gases, and next time we're going to talk about maybe compressibility. So gases, or maybe today. So gases. Ideal gas law. Think 3.6. Ideal gas law. So ideal means inviscid, non-viscous, zero viscosity. Gas means, please, this is gas. It's not a liquid. It's a gas, like air, oxygen, nitrogen, even R134. Low means it's always correct. Always correct. Low, different from theory, from the hypothesis. So low, always correct, like first of thermodynamics. If you have a gas like argon, it's ideal gas. Argon is ideal gas in the gas phase. This equation is always valid. We have two formulas. PV equal mRT. We have PV equal nRT. These are the two ideal gas law. Sometimes we call them equation of state. Sometimes we say equation of state. It means gas law. This is pressure in Pascal, volume meter cube, mass in kilogram. Sometimes we write this either P nu equal RT, specific volume. Sometimes we write it P equal rho RT, because 1 over rho, 1 over nu is rho. So here, so mass over volume is rho, or volume over mass is specific volume. So this is the same formula as this. So this is the general one. Mass in kilogram or gas constant. Gas constant. For every gas, it's joule or kilojoule per kilogram Kelvin. Joule better because this is everything in the standard units. Temperature is in Kelvin. Must be Kelvin. Must be Kelvin. I will say it forever. This is must be Kelvin. Always use Kelvin for SI units. This is Kelvin. Make sense, guys? You have seen this equation from high school, correct?
Correct.
The same equation in universal form. This is called universal form. The same form. This is exactly the same as this. But here, pressure, Pascal, volume is meter cube in units, and N number of mole. And this is universal gas constant. Universal gas constant. This is universal gas constant. This one. Sometimes use R bar or RU, which is means universal gas constant. Let me do some trick. 1 second, guys. Better like this or what? This is better? Guys, can you see that? Can you see the board? Can you see the board or no?
Yep.
There is any reflection or something? Okay.
It's super blurry.
It's clear or not? Yes or no?
No.
It's not clear. Okay, let me make it taller.
No, I can't. I can't read it.
Yeah, it's really blurry.
Give me 1 minute. 1 minute, guys. I'm gonna touch the ceiling maybe. 1 minute. If my laptop is broken, I'm gonna let you pay. Okay, pay for that. Okay,
No problem, man.
man. Thank you, dude. So PV equal now it's clear.
A
Now
little
it's clear.
better,
Okay.
kind of.
So P is pressure, V is volume, N is number of mole, RU is universal constant. It's kilojoule per kilomole Kelvin. This is kilomole, for example. This is mole, and this is Kelvin, of course. So these two equations exactly the same. Exactly the same. But here is kilogram, this is kilomole. So what is this? So many people, unfortunately, do not like number of moles. Guys, number of moles is so simple. It's like this. I have a space like this, V. You said, for example, this is length by width by height. If it's bigger, you said, that's still length by width by height, but it's bigger. Length bigger, W bigger, height bigger, correct? This is called volume. Mass, something else. Mass, let's say you have 1 kilogram of copper. You have 1 kilogram of air, huge volume, but the mass is the same. Oops. Can you see me, guys?
Yeah.
So this is 1 kilogram, small amount, and this is huge volume, but the same mass. So mass is different from volume, correct? Number of mole exactly the same as mass. Exactly same as mass, exactly. In other words, there is a bad guy, there is a scientist, his name Avogadro. He said, I'm gonna count, give you a number, which is 6.023, 6.0, I don't know, 22, 10 to the 23, number of molecule per 1 mole. He said, I'm gonna go to any material. He says Avogadro number. Any material. If I found I have 6.022 10 to 12 23 mole per kilogram, molecule per kilogram, molecule or moles or molecules or atoms, it depends on the material, it's 1 mole. So if I give you water, I give you this number, it's 1 mole. If I give you like this, some water, like some air, it's huge like this. This is 1 mole. Copper is some small like this, exactly like mass, exactly, but number. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, until this number. So this is mole. This is called here the same number, but these are very heavy. Everyone like very small, close to each other like this. They are so small and close to each other. Here is big gap. This is air. So mole is exactly mass, and the relation called M or MW, molecular weight, which is M over N. And this is constant for any material. For example, water, H2O. Molecular weight is 18. For every 18 kilogram of water, you have 1 mole. Every 1 mole is 18 kilogram of water. Molecular weight for any material is constant. It's how many kilograms to how many moles. Constant number for material. Air is 28. So I have 28. Whatever material, it's how many kilograms per kilomole. Molecular weight. And it's constant number. So moles is exactly mass. Exactly like mass. Not a volume. It's exactly like mass. Representing mass. That's why these two equations exactly the same. PV equal MRT or PV equal N R universal T. PV equal MRT. So these two terms is exactly the same. So M R equal N R universal. This is joule per kilogram Kelvin, joule per kilomole Kelvin. That's what مطلوب here. So it's M over N equal R universal over R. And this is molecular weight. This very important relation. This is kilogram per kilomole. This is here per kilogram. This is per kilomole. That's why it's reversed. So any material has molecular weight. For example, oxygen. What is the molecular weight for oxygen, guys? 16 maybe? Correct?
Yeah.
So it means we have 16 kilogram per kilomole. If you have 1 kilomole of oxygen, it must be 16 kilogram. 16 kilogram. Okay? Make sense? For every material, we have one value molecule. Any material. Ratio between mass to number of mole is always same for one material. For example, molecular weight of air, I think is 28 kilogram per kilomole. If I give you 1 kilomole of air, it must be 28 kilogram of air. This is called molecular weight. It's mass, M small, over number of mole. Sometimes use N capital N small. R universal. Sometimes use R, like this, the book, over R, which is, this is gas constant. This is universal gas constant. Again, let's see what happened. Universal gas constant, it's always 8314 joule kilomole over Kelvin. It's always like this. Always 8314, 8314 joule. It means if I give you 1 kilomole of any gas, it takes exactly this energy to raise 1 Kelvin. If I give you 1 kilomole of air, of oxygen, argon, gas, any gas, any gas, any gas, it takes exactly 8314 joule for this 1 kilomole to raise 1 Kelvin. If you want 2 kelvins, multiply by 2. 3 kelvins. So this is to increase 1 degree. For any kilomole of any gas, you need this energy. Is it hard?
You're cutting out a lot, Professor.
Cut a lot? Net is not good? How about now? How about
Better.
now, guys?
Yeah, it sounds a little better.
So for any gas, to raise 1 degree, you need this number of joules. You need heat. You need joules, which is 8314. But this guy, no, you don't know. It depends on the gas. So it's R universal over molecular weight. This equation. So it's R universal over molecular weight. So if I give you air, you said, oh, it's 8314 divided by 28. So this is R air. If you want to get, for example, R air, it's 8314 kilojoule per kilomole Kelvin divided by molecular weight, which is kilogram per kilomole. So remainder is 481. No, this is 287 kilojoule. Actually, joule. This is joules per kilogram Kelvin. This is R air. Okay. I think oxygen is 16, guys. Oxygen is 16, not 8. So this is our air. This by 28 kilogram per kilomole. This is kilojoule, yes, joule. So this is 287 joule per kilogram Kelvin. Go ahead, please open the table again. I'm gonna close here now for 1 second. Share with you the tables again. Where are the tables? I think the tables are in here. Where are the tables? Yeah, here. I found it. Okay, here. So if you go up, please up until table A1, A2. Look at table A1. Can you see table A1 with me?
Yes, we see it.
The first substance, which is gas, we don't have formula. This is because it's a mixture of something. We call it pure air, yes, but it's a lot of things like nitrogen, like oxygen, 70%, 78% nitrogen, 79% nitrogen, 21% oxygen, some carbon dioxide. So this is a molecular weight. It's about 29. Sorry, 29. It's 287 joule per kilogram Kelvin. This is a gas constant. Can you see, guys? Or 0.287 kilojoule per kilogram Kelvin. Okay? It gives you critical point, the critical temperature, critical pressure, critical specific volume. This is the data of air. The same for ammonia, NH3. The same for argon. This is alphabetic. That's why it's like this, but we are lucky air is the first. Benzene. If you go down, below down here, for example, you can find ethane, kerosene. These are important fluid. Nitrogen was mostly air, very close. You see this number, for example, so close to the air because it's mostly the air, mostly what? Nitrogen. That's why you see this value so close to this value. Oxygen is here. Okay. So something in between is the air because air is mixture between mostly oxygen, mainly nitrogen and some oxygen. Okay, guys, you see what happened? Okay.
Yep.
Yes, makes sense.
Anyway, so these guys at kind of standard temperature and pressure, if we assume that's total ideal. However, for at some conditions, these numbers are not the same. For example, table A to B, you will see, for example, the R or the CB minus CV, which is R, is different with temperature. This is function of temperature. We're going to discuss this right now. So sometimes, when this is the case, some of these properties are not constant. They need to be function of temperature. Okay. So we can give some problem. Actually, I have problem for you in page 42. You can solve it yourself. It's a simple problem. Just to get the volume, substitute in this equation, PV equal nRT. You can get. Sometimes we use N uppercase, like this N. Sometimes uppercase, sometimes lowercase. But most of the probably you can use uppercase. This N uppercase sometimes. Uppercase N number of moles in kilogram. If R universal, kilojoule per kilogram. Okay, let's take the last definition, which is compressibility factor. This is an important problem. You're gonna see it in midterm, in the final maybe. This is called compressibility factor. I think the first following section. 3.7, yes. 3.7, compressibility factor, Z, a new definition. Can you see it, guys? Can you see it, guys? 3.7.
Yep.
This compressibility factor is so important for us, and I'll tell you why. Z is P V over R T. This is specific volume. This is temperature. This is universal gas constant. This is gas constant. It's like SI units. Okay, P pressure, V specific volume. This is a correction factor to ideal gas law. It means if you have the PV diagram, let's say TV diagram like the TV diagram, TV diagram, and you know exactly it's like this. This is the TV diagram, for example, for water, for example. This is correct. This is temperature is pressure is constant, like 1 atmosphere, for example. Okay, guys? Okay?
Yep.
So let's take a point here. Let's take a point here, this point. It has P, it has V, it has T, it has U, H, it has all properties. Of course, there is no X for this point at superheated vapor. I have a question for you. This point is gas or liquid?
Liquid.
This is superheated region. Superheated means vapor. This is liquid here. Compressed liquid. Here mixture, here superheated. So this is completely gas, like air, like vapor. Any something is gas phase. So this is gas phase. But it's not exactly ideal. I don't know. So we cannot do something. Let's multiply P, V over R of this like gas, T. And R, it's R universal over molecular weight. Let's say this is water. Water is, molecular weight is 18 kilogram per kilomole. So what I'm gonna do, I'm gonna get R universal. I know water is not gas, yes. But when it goes to vapor, it's gas, yes. But does it ideal or not? Does it follow law or not? So if this ratio is piece pressure, time by volume, divide by T in Kelvin, in Kelvin. Yes, tables are in Celsius, but you must substitute by temperature in Kelvin. And this gas constant, like universal molecular weight, if this value became 1, this is perfectly ideal gas law. In reality, it's not 1, it's like 0.9, 0.8, so we call it compressibility correction. Simple. So if this Z became 1, you are ideal gas. Okay. For some fluid, when it goes to gas, they are very good into to gas, to be considered as. So in reality, what happened? We have a very good region here. We can consider Z approximately 1 in superheated vapor. Superheated vapor, like air. We are living now in the superheated vapor of air, correct? If we decrease the temperature of the atmosphere, it became liquid. Air became liquid. If we heat it up, it's gonna be vapor or gas. We are living now in the superheated vapor of air region. So now we have a very simple formula like this. That's a very good formula. Imagine that you have a state, we have PV, and you don't have the data in the table. This you can easily get temperature if Z approximately 1. How about if I can give you Z for any fluid? So this T can be get analytically if this is given, correct? So we said we have 3 datas. Table, like table A4, A5, A6. These are tables that give me 2 inputs, I give you the third, correct? We have charts, like for example, look at figure A8 or A9. This is a chart. You can go with 2 variables, you get the rest. we can give equation like this equation, like PV equal RT. This is very good equation, a very good equation. It can speed up a lot our calculation. Nelson and Nelson chart. If you go to table A15, please, there is something called Nelson chart. Please, everybody open table A15. It's a chart. A15. A15. I'm gonna share it with you guys. If you go down below here, chart's called A15. It's a Nelson chart for compressibility factor for different values. It's a very beautiful chart. A15. Here, this chart. Can you see this chart? It's called compressibility factor, Z. Can you see it? This axis is compressibility factor. Z, PV over RT. This is the reduced pressure. Here we have different reduced temperature and volume. Reduced temperature and volume. So the chart like this. Can you see this table? This table is so good. These values. Can you see this, guys?
Yes.
Great. Let me write it down here in the board. Unfortunately, we have huge values of pressure and temperature, sometimes volume, sometimes small value, sometimes huge value. Very huge. Like for air, for example, we have 220 atmosphere, the critical point. It's so big. We have very huge range. Smart people do this. Do something called reduced units. P reduced or PR is equal P over P critical. T reduced over T critical. The same for specific volume reduced. We can use just R for simplicity. Use R. Nu over nu critical. So for any fluid, if you go to table A1 again, table A1, this value given in table A1. If you give it table A1 again, you'll see these values are given, correct? Critical temperature, critical pressure, critical specific volume. Critical pressure, critical temperature, critical specific volume are given for any fluid in table A1, correct? Correct?
Yes.
Yes.
So if I give you a state, I give you temperature, and a volume. And you know exactly, you have like these values. For example, now, any of two, these two. This is called a state. So you can get P reduced, T reduced. So you can go to this chart by two inputs, any two inputs. We usually have two independent inputs. Like for example, P reduced and T reduced. These are T reduced. T reduced. Let's say P reduced was 0.5. You have 50% of critical pressure. Let's say T reduced was 0.7. This here, 0.7. You have T reduced equal 0.7. You have 70%. This is in Kelvin. This is in Kelvin. Everything in Kelvin. Everything temperature Kelvin. I'm repeating that over and over. And I'm sure one of you or more, sometimes many, substitute with Celsius. I don't know why. These are in kelvins. Any ratio, any multiplication of temperature, Kelvin. Sometimes, if it's difference, you can use Celsius or Kelvin. But I recommend use forever Kelvin, just without any noise. So if you have the B reduced, the pressure, if you have T reduced, temperature, like you have this pressure, let's say, for example, 110 divided by 220, it's half ratio. This is, let's say, 170 or 180 divided by T critical, which is 370, for example, you can get T reduced, or 300 or 400, you can get reduced in Kelvin. So you can get this value, which is 0.8754. You can get a value of Z. You can know exactly how far you are from ideal gas law. How far you are from ideal gas law. This Z, 0.87 is Z. Let's go back to chart. in 2 minutes, we're gonna take a quiz. So be aware. So we have here, go inside. The x-axis be reduced. Can you see? 0.5. Can you see that? I'm gonna go vertically like this. And 0.7 is here. And you can go horizontally, you see that Z is 0.8 something. Can you see, guys? Can you see, guys?
Yeah.
Yeah.
Yes.
Yeah, you need to practice a lot. We're gonna take a problem in the beginning of next lecture. Now it's a quiz. Okay, guys, give me 1 minute. I'm gonna confirm the quiz for you, and go ahead and please make sure you are uploading the quiz. I don't know, did you read my notes or not? But you need to upload the quiz as soon as possible. Find a fast way to the quiz is now, I think, available for you. Can you see the quiz, guys?